Talked about the definition of the nodes, the definition of the edges, and features. We said that if we use one type of node, we are defining homogeneous graph, and if we use more than one type of node, we are defining heterogeneous graph. Moreover, we talked about the edges, and we said edges describe a link between the nodes. We said mathematically we could use adjacency matrix or weight matrix to define the edges. Furthermore, we said that the nodes could carry additional information, which are shown in the form of features. We talked about two types of graph, directed and undirected graph, and we said that in the directed graph, the relation between the nodes is directional and the matrix is asymmetric, while in undirected graph, there is no direction within the links, and therefore the matrix is symmetric matrix. Now we want to talk about how to store the graph data and information. Let's start with this homogeneous graph, which includes 4 nodes. To make things easier for ourselves, let's start with the definition of the nodes by giving them some labels or names. In this case, I'm using numbers 0 to 3 to define the name for each node. So we have node 0, node 1, node 2, and node 3. One way to define the information for the graph is to use something known as edge list. This edge list allows us to store data about the graph and the links that connects the nodes in the graph. So the way we use the edge list is by defining 2 elements in every row. Each row describes a link for 2 nodes, where the first element in the link is the source node and the second element is the target node. Let's take a look at this example. For the node 0, you can see that there are 3 connections, node 1, node 2, node 3. Therefore, in the edge list, we could use the notation of 0, 1, 0, 2, and 0, 3 to define all the relations for the node 0. For the node 1, there is only one connection, and therefore we only have 1 and 0. For the node 2, we have connection with 0, connection with itself, and node 3, therefore we can write it as 2, 0, 2, 1, and 2, 3. Lastly, for the node 3, we have 3, 0, and 3, 2 as the 2 connections of the node 3. First thing that I want you to point out is that this edge list considers the direction. In the case that I'm showing in here, we are representing undirected graph because there is no arrow defining relation between nodes. However, in the edge list, we are defining this relation twice. For example, for 0 and 1, and then 1 and 0. This way, the edge list stores information about the direction of the edges. Another way to store data in the graph is to use the adjacency matrix which we introduced earlier. Consider A as our adjacency matrix. Adjacency matrix is a binary matrix which describes whether there is relation between nodes or not. At every row of adjacency matrix, we compare one node with every other node including in itself. If there is a connection, we will put the value of 1. If there is no connection, we will put a value of 0. Let's take a look at first example. For the node 0, we have connections with node 1, 2, 3, and there is no self-connection. So in the first row of the adjacency matrix, we can put 0 for 0 and 0, 1 for 0, 1, 2 for 0, 2, and 3 for 0, 3. Let's take a look at another example. Let's see the node 2. Node 2 has connection with node 0 and node 3 and itself. Therefore, we have a value of 1 for nodes 2, 0, 2, 2, and 2, 3, and value of 0 for the node 2, 1. To illustrate a specific element from the adjacency matrix, we could use the notation of Aij, where Aij is from node I to node J connection. First thing that you could notice from the adjacency matrix is that the adjacency matrix is a square matrix. This is because at the rows we have the same number of the nodes that we have as the columns, and we are comparing the nodes with themselves and with the other nodes. Next important information is that A is symmetric if the graph is an undirected graph. This is because in an undirected graph, the relation between 0, 1 is the same as 1, 0. We could replace this binary representation with different float numbers instead of the values that are set as 1. And in this case, we are defining the matrix as such. This means that although 0 still shows no connection between the nodes, we could define how powerful the connections are, and therefore we could use float values to define the strength of the connection. If we use this such matrix, we are defining a weight matrix. In here, we refer to it as W. So now it makes sense to see why we can have either A or W defining the edges of our data, because they are different only if we care about the strength of the connection.